Hi, we are students of Civil Engineering UiTM Shah Alam. This is a project of ECS 536 Special Concrete. In this video, we will discuss about geopolymer concrete. My name is Muhammad Iqwan bin Marwan.
My name is Muhammad Fahan Farihin bin Alfian.
I am Nur Syafiqah binti Mat Rodi.
My name is Nurul Syafiqah binti Syahrul Nizam.
Before that, let's watch this video first.
Concrete is one of the most widely used substances on Earth. It has allowed us to tame nature and is the foundation of modern development. However, it is causing our blue and green world to become grayer by the second. In 2020, scientists estimated that human-made materials reached 1.1 trillion tons, exceeding the mass of all living things on the planet, including people, bacteria, plants, and animals combined. One of these human-made culprits is Portland cement, the key ingredient in concrete that binds all the other ingredients together. Its production is very energy-intensive, it emits carbon dioxide and other greenhouse gases, it causes soil erosion and noise pollution, and it adversely affects air quality. Researchers around the world are trying to find an alternative to traditional cement and concrete that is less destructive to our planet. One very promising material is geopolymer cement. It completely replaces Portland cement with waste industrial products. It can also be much stronger and perform better than traditional cement.
The issues related to conventional concrete or Portland cement concrete is CO2 and greenhouse emissions. The production of Portland cement leads to release significant amount of CO2 and other greenhouse gases into the atmosphere. Next is waste product. Waste products are difficult to dispose and affect the environment if left untreated. It would be good if it can be used in making concrete. The last one is noise pollution. Processed cement manufacture will lead to noise pollution. They also have other issues or problems such as air quality, soil erosion, and many more.
What is geopolymer concrete? Geopolymer concrete is a type of concrete that is made by reacting aluminate and silicate-bearing materials with a caustic activator. Geopolymer concrete are prospective concrete which possess remarkable physicochemical and mechanical properties. It also known to exhibit excellent performance with respect to fire resistant, acid resistant, and show the good result in testing material. As you can see, there are three basic forms of geopolymers, and their structure shows that the reaction mechanism of geopolymer and normal base concretes. What is the advantage of geopolymer concrete? Geopolymer significantly lower carbon dioxide emission than OPC concrete, which up to 90%. Geopolymer concrete give better thermal insulation properties that can reduce the global warming. Next, it providing a viable use for waste material which are often disposed in landfill. And geopolymer concrete also give benefit to environment which are the good strength of durability properties that lead as sustainable concrete.
Constituent of geopolymer concrete. Geopolymeric material can be produced from raw material or industrial byproduct that have rich aluminosilicate composition. The source of material used for geopolymerization can be single material or a combination of various types of material. Among the potential aluminosilicate-based materials such as coal fly ash, silica fume, and alkaline are the most widely used. Mechanical properties such as compressive strength, tensile and flexure strength, and modulus of elasticity are the key parameter of evaluating the performance of concrete and to predict the service life. The mechanical properties of geopolymer concrete have been reported to be equal to or better than those exhibited by equivalent Portland cement concrete. Among all the concrete properties, compressive strength is one of the most important properties of hardened concrete. According to the Vance-Jarvis, it was also revealed that the calcium content in fly ash played a significant role in strength development, and final compressive strength as higher calcium content resulted in faster strength development and higher compressive strength. A study by Zhu and Van Deventer to produce geopolymer with a higher compressive strength, source material which possess high reactivity are required. The author have further reported the significant importance in the compressive strength can be achieved when a calcinite source material such as fly ash is added as compared to non-silicate calcium material for geopolymerization. Although concrete mix are proportionate on the basis of achieving the desired compressive strength at the significant age, however, the determination of tensile and fracture strength is helpful in mitigating the cracking problem, improving shear strength prediction, and minimizing the failure of the concrete in tension. Geopolymer concrete are reported to have comparable or higher tensile and fracture strength value than the equivalent Portland cement concrete. As in the case of compressive strength, geopolymer concrete develop very high tensile and fracture strength at early age with gradual increase over time. Harjito and Rangan measured the tensile strength of heat-cured fly ash-based geopolymer concrete by performing the cylinder splitting test on 150 times 300 mm concrete cylinder. The test indicate that the splitting tensile strength of fly ash-based concrete is a fraction of the compressive strength, as in the case of Portland cement concrete. Modulus of elasticity is one of the important mechanical properties of concrete used for designing and analyzing the strength and service ability of concrete structure. In particular, knowledge of this factor is necessary when the deformation of the different structural elements of a structure have to be calculated. Several researchers have studied the elastic characteristic of geopolymer concrete. Most of the research studies have reported that elastic modulus of geopolymer concrete have lower than the OPC concrete. According to the research by Fernandez Jimenez, also found that the addition of soluble silicate in the alkaline solution although improved the modulus elasticity in fly ash-based geopolymer concrete. However, this improvement was not significant and the alkaline activated fly ash-based concrete show a much lower static modulus of elasticity than expected.
Discussion. Figure 1 shows as the activator slowly permeates through the newly formed coating, the reaction continues at a slower rate, and the compressive strength continues to gradually rise but does not vary greatly with the age of concrete. This contrasts with the strength development behavior of OPC-based concrete, where the hydration process extends over a length of time and gains strength with age. Figure 2 shows that Hardy-Gito et al. Reported that with the increase of activator content and consequently increasing the activator or fly ash ratio up to 0.4, the compressive strength of the resulting geopolymer mortar was increased. However, increasing the activator or fly ash ratio to 0.45, there was a decrease in the compressive strength of geopolymer mortar. This was possibly due to excess of OH concentration, which consequently decreased the strength of geopolymer mortar. Olivia and Nikras reported that both splitting tensile and flexural strength of the geopolymer concrete increased with increasing concrete age. The splitting tensile strength value of fly ash-based geopolymer concrete were comparable or higher than those of OPC-based control concrete. The tensile strength of optimal mix T10 was 8 until 12% higher than that of OPC concrete at 28 and 91 days. This could be due to the effective bonding between the geopolymer matrix and aggregate. The flexural strength of the geopolymer concrete was found to be 1 until 1.5 times higher than that of the OPC concrete at 28 and 91 days. Lastly, Hardicito and Rangan reported that the modulus of elasticity and Poisson ratio of fly ash-based geopolymer concrete were of the same characteristic possessed by OPC concrete. Also, the measured stress-strain relationship of geopolymer concrete fit well with equation designed for Portland cement concrete. The measured value of the modulus elasticity of geopolymer concrete with compressive strength in the range of 44 until 89 MPa were similar to those of OPC concrete, yet the measured value were at the lower end of the value calculated using the current design standard as shown in the table. This could be due to the type of coarse aggregate used in the manufacture of the geopolymer concrete. However, the Poisson ratio of fly ash-based geopolymer concrete with compressive strength in the range of 44 to 89 MPa fallen between 0.12 and 0.16, which were quite similar to those of OPC-based concrete. In conclusion, geopolymer technology has become a viable technology, and geopolymeric materials are considered as the cement of the future due to their low ecological impact and relatively high yield from raw materials. Second, a number of studies have been done on the performance of geopolymer concrete, which shows several advantages over conventional concrete. Third, geopolymer concrete can improve the properties of structure itself and develop sustainable of structure. And last but not least, geopolymer concrete get more stronger parallel to the increment of the fly ash percentage. That's all from us. Thank you.